So in this section, we're going to do a few problems based on what we have learned so far. Okay. A car of mass 1000 kg travels round a level curve of radius 40 meters. So if the maximum frictional force that can be exerted upon the car by the road, determined by the coefficient of friction between the tires on the road, is 7,000 newtons, how fast can the car travel without spinning out? Okay, so I'm just going to make a little diagram to sketch what I know. Let's say this is a circle in which my car is traveling, and let this be the center of the circle. Then we know the mass of the car out here, m, equals 1000 kgs. Okay. Radius, r, and we know that the radius is 40 meters. And we know that the frictional force maximum is 7,000. We know that that frictional force must be equal to my centripetal force, okay, which is mv squared over r. And we're asked how fast the car can travel. That means we want to find that value of v, yeah? So I'm going to insert some values here. So this frictional force equals 7,000 units, yeah? We know m, we know r, so it should be perfectly possible to calculate v, right? I want you to try to do this and compare your answer with mine on the next slide. So you should get v as 16.7 meters per second. Okay, straightforward, but you need to be able to put your concepts together. Just checking for your concept and formula application. Let's do another one. Curves on some test tracks and race courses, such as Daytona International Speedway in Florida, are very steeply banked. This banking, with the aid of tire friction and very stable car configurations, allows curves to be taken at very high speed. Calculate the speed at which a 100-meter radius curved bank at 65 degrees should be driven if the road is frictionless. Okay, so now we're not allowing for any friction, but just based on that angle, we have a component of the force. So you're going to go look back at our leveled and raised tracks. And you'll see that in the raised tracks, we had a relationship of tan theta equals v squared over rg. Just to remind you, I have given you the formula here, okay? But this will normally not be given in the problem. You need to know what to look for. So we know theta, we are asked to find v, we know r, and we know g, yeah? So this is perfectly possible for you to solve this just using this formula. And you should get 45.8 meters per second. This is without friction. If you add in friction for the track, you can go even faster, yeah? Okay. Lastly, in this section, we come to looking at a loop-de-loop, which is a vertical circle. So here we have a vertical circle. Okay, you might have been on such rides. And the question is, why don't you fall off? You would fall off if your downward force, which is mg, right at the top, so we're looking here, okay? And let's maybe draw in that force. So at the top, you have mg acting downwards, yeah? And you need to provide centripetal force here, yeah, to keep in the circle. If your mg is greater than your centripetal force, you're just going to fall straight down. Yeah? So if mg is equal to the centripetal force, you will stay in the circle. Okay, that means mv squared over r, which is my centripetal force, must equal mg. Yeah? 2 m's cancel out. V squared over r is my g, or the velocity with which we can take this curve is rg, okay, or the square root of rg. So we need to take square root of both sides. This little r and the uppercase r are the same in this case, okay? So let me just make that a little more explicit. That's right, R equals uppercase R, which is in this diagram, okay? So substitute that in, you get square root over RG. That means the bigger the R, the bigger the velocity that's required to take this curve, given that G is fixed, yeah? Okay, so the minimum velocity is determined by this. Okay. In general, you have a problem-solving strategy for these kinds of problems. You're going to make or sketch a diagram after reading the problem. You're going to choose a set of coordinate axes, which in rotational motion is always along the radial and tangential directions, okay? So you're going normal to the plane of motion, okay? For the axis, it's usually normal to the plane of motion, okay? You're going to find the net force towards the center and equate it to the centripetal force required. You're going to use Newton's second law, F equals m into a, whether you're looking for centripetal force or acceleration, okay? And you're going to separate out those two directions, radial and tangential. Along the radius, you'll have your centripetal acceleration. Yeah? Then you solve for the unknowns.